Hi, in this video, we are going to start a new section in the course. This is the section on recursive sequencing. So, advanced sequences. In this video, we look at recursive sequences, and in the next video, we look at periodic sequences. So, let's get to the definitions. A sequence AN determined by initial terms, and an equation of the form a n plus k is equal to some function of a n plus k minus 1, a n plus k minus 2, and so on till a n. Some function of these variables, the other lower order terms of the sequence, is called a kth order recursive sequence. So notice what we have defined the sequence as. So here we have a n plus k. So for example, a n plus 3, if you say that it is a n plus 2 a n plus 1 minus a n. So here a n plus 3 is written as a function of these three lower terms, right? So that will be a third order recursive sequence. As long as you can express a n plus k as a function of lower order terms till a n, we get a kth order recursive sequence, right? So if we have a basic equation that defines a recursive sequence like this, C1 a n plus k minus 1 plus C2 a n plus k minus 2, and so on till Ck a n plus some function of n. This is a linear kth order recursive sequence. Here C1, C2 till Ck are constants, and Ck should not be 0. And Ck is not equal to 0. If Ck is 0, then this term is missing, then this does not fit our definition of a kth order sequence, right? We'll have to adjust it a little bit. It might be k minus 1 order or something. So if you have an equation like this of this form, then this becomes a linear kth order recursive sequence. Why is it linear? Because there is no squares and all. Every term, every lower order term of the sequence has power or 1, right? So degree 1 everywhere, right? So if there are squares and all, it becomes a non-linear recursive sequence. So mostly in this video, we'll be worrying about linear recursive sequences because those are the ones that are more common. And from an Olympiad perspective, that is what you need to know. So one more special case here, if f of n is 0, therefore the main equation becomes a n plus k is equal to c1 a n plus k minus 1, c2 a n plus k minus 2, and so on till ck a n. And that's it. There is no f of n terms. And this is called a kth order homogeneous linear recursive sequence. Homogeneous linear recursive sequence, which is quite a mouthful, but that is how the definition is, right? Now, if you take some examples of, let's say, an AP, so any arithmetic progression will satisfy this relation. A n plus 2 is equal to twice of a n plus 1 minus a n, right? So here, this is a second order linear homogeneous recursive sequence, right? Now, why is this an AP? It is obvious that the first and the third terms are adding up to twice of the middle term, right? So this is an AP. And a GP would be written as this: an plus 1 is equal to r times an. So this is a first order linear homogeneous recursive sequence, right? So these are the simple sequences that we have seen in the past. Now we want to basically our objective is to look at this equation an plus k is equal to c1 an plus k minus 1 plus c2 an plus k minus 2. And this general kth order homogeneous linear recursive sequence, we look at this and we want to be able to find the general term of this, right? We want to find how the general term is as a function of n, right? So that is the goal. And there are a couple of theorems that help us here, right? So we look at the theorems, we'll not do the proof right now. The proof is a little advanced in the sense that it uses some of the concepts that we employ in the solution of linear differential equations. So the solution is similar to how we solve linear differential equations, where we guess a solution and after that we put it in the equation itself and uh, manipulate it with the initial conditions in order to come at the final solution. So it's sort of similar. So I'll just tell you how to solve it. So basically, first of all, the equation an plus k is equal to c1 an plus k minus 1, c2 an plus k minus 2. This is our base equation that we want to solve for an. We want to predict what an will be. Now, looking at this equation and the pattern here, c1, c2, and ck are all constants. We will construct a new equation. This is known as the characteristic equation of the recurrence. Characteristic equation for the recurrence. So what is this characteristic equation? It looks like this. Here we will say x bar k is equal to c1 x bar k minus 1 plus c2 x bar k minus 2 and so on till ck x bar 0. So this equation is our characteristic equation. Notice that the pattern of this equation is exactly similar to the pattern which defines our recurrence. So here it was an plus k, here it is x bar k. This is k minus 1 above the n, so it is x bar k minus 1 and so on. You can see the pattern. So the theorem says, the first theorem that we look at, it says that if the roots of the characteristic equation are lambda 1, lambda 2 till lambda k. Notice that the characteristic equation has degree k. This is the degree k polynomial equation. If the roots of this equation are lambda 1 to lambda k and the roots are mutually distinct, there are no common roots. Every root is different from the other, and these are the k different roots. Then the sequence an has the general formula of an is equal to a1 lambda 1 power n plus a2 lambda 2 power n and so on till ak lambda k power n. Here a1, a2 till ak are constants determined by the initial values of the recurrence of the sequence, by initial values of, let's say, the first term, second term, third term, and so on till kth term. If you know the first k terms of the sequence, they will give you enough equations to solve for these k constants, right? Because we know the general form of each term, we can substitute the values of a1, a2, ak, and we'll be getting k equations which will help us find these k constants, capital A constants, right? So the theorem 1 is basically saying that if we form the characteristic equation for our recurrence, if the roots of that equation are mutually distinct and these are the roots, the general term of the recurrence will be of this form. So right now we are going to accept the theorem without any proof. Later when we do some examples, we'll realize that the theorem works fine, right? Now the other case is when the roots are not basically mutually distinct, right? So our preliminary equation was this. This was a recurrence equation. And our characteristic equation was this. And this characteristic equation has roots lambda 1, lambda 2, lambda s, where s is less than k. Why is this less than k now? Because some of the roots could be repeated roots. Because we have repeated roots, therefore we will not have all k roots, right? So these are the roots, these are s roots, and each root, the multiplicity of each root is lambda I. No, each root lambda I is ti, where 1 is less than equal to I less than equal to s. So basically, lambda 1, there are how many copies of lambda 1? T1. Lambda 2, there are T2 copies, and so on. Lambda s, there are Ts copies. Obviously, T1 plus T2 plus Ts should add up to k, because total number of roots have to be k, right? In this case, the solution is not the simple solution that we had in theorem 1. In this case, an will be given by a1 as a function of n multiplied by lambda 1 power n plus a2 as a function of n multiplied by lambda 2 power n, so on till as a function of n and lambda s power n. So this right now looks very similar to the previous solution, but remember earlier these were constants a1, a2, ak, right? Now we have functions of n here, right? So what is this function of n? So each of the ain, this function of n can be written as b1 I plus b2 I n plus so on till bti I n to the power ti minus 1, with I going from 1 to s, and your bji are constants which can be determined from the initial values, So what does this mean actually? So what this means is each of the functions themselves. So suppose you have the first root had multiplicity 1. So ti was equal to 1, let's say. So what will be a1n? So a1n would be b1 plus b. This power goes till ti 1 minus 1, right? So this sequence is constructed. So I will just do it on the next screen. So suppose my characteristic equation, which was this equation, x bar k is equal to c1 x bar k minus 1 plus c2 x bar k minus 2 plus ck x bar 0. Let's say for the purpose of this question, our k value is 4 and we have roots lambda 1, lambda 2, lambda 3. These are the three roots. This is 1, and these are 2. So basically the multiplicity of the roots is 1, 1 and 2, right? So basically you have to solve this characteristic polynomial and you might get 4 roots, 1 lambda 1, 1 lambda 2 and twice lambda 3, right? In this case, I will say my an will be a1n lambda 1 power n plus a2n lambda 2 power n plus a3n lambda 3 power n. And now I have to define my a1n, a2n and a3n, right? So my a1n, the multiplicity of A1 is simply 1. So the way we construct it is we write B1 plus B2 n plus B2, B3 n square, and so on till BTI and n power Ti minus 1, where Ti was the multiplicity. But in this particular case, the multiplicity Ti, T1 is simply 1. So we don't need to go so forward, right? We'll just get B1 because B2 n to the power 1 minus 1 is 0. You cannot go ahead of this term. There is only one term here. So it is simply B1. Similarly, A2n will be simply B2. But A3n will be basically B1 dash plus B2 dash n plus, actually here the power will go up to 1, right? This will be a linear function. So there is no other term after this. So what we have is these are the functions of A1n, A2n, and A3n. So I will say my an can be written as B1 lambda 1 power n plus B2 lambda 2 power n plus B1 dash plus B2 dash n lambda 3 power n. This is because of the repeated roots nature here. So that is what theorem 2 basically says. You have to construct functions of n here, and these functions of n will be growing in degree, and it will be up to degree Ti minus 1, polynomial of degree Ti minus 1, where Ti is the multiplicity of that root in the characteristic equation. Now, enough of the theory part here. We have to actually learn how to apply these theorems in actual recurrence problems. And many times you actually don't need to find the anth general expression of an while solving Olympiad problems. So many questions we won't even get to that stage, but sometimes you may need to. So that's why we have discussed these two theorems. So let's move on to the questions. The first one is this: let a sequence an satisfy a1 is equal to pi by 6 and an plus 1 is equal to arctan sec of an. We have to find a positive integer m such that sine of a1 multiplied by sine of a2 multiplied by sine of am is equal to 1 by 100. Okay. So this is how our sequence has been defined. So what we can say is an plus 1 is arctan is basically tan inverse sec of an. So we can take tan on both sides and you get tan of an plus 1 is equal to sec of an, right? Also from here, because the range of tan inverse function is minus pi by 2 to pi by 2, we know that an plus 1 lies between minus pi by 2 to pi by 2, right? Tan inverse function is only defined in that range. And from here, we can say that sec of an is actually greater than equal to 0. So therefore, an plus 1 must lie actually between 0 to pi by 2. It could possibly have been this much, but we know that sec will become positive here because the starting point of the series is a positive term. So a2 will become also positive. So an plus 1 will actually lie between 0 to pi by 2, right? Now let's look at the general relationship here, and we can say tan square an plus 1 is equal to sec square an, which is 1 plus tan square an. And from this, what we are getting is that tan square an plus 1 minus tan square an is equal to 1, right? which is has a very nice nature. It is telescoping. So if you put n as 1, 2, 3, and so on, and keep adding it, you will be able to come to the conclusion. If you just take n terms, only the first and the last terms will remain here, right? And this side it will become n. So by adding different copies of this will become a telescoping series, and you will end up getting this tan square an plus 1 minus tan square a1 is equal to n, right? This is what you get. Now, here I am getting a function of an plus 1 here in terms of n. So I want an term. I don't want an plus 1 term. So I will replace n plus 1 with n in this equation. And what we'll get is tan square an minus tan square a1 is equal to n minus 1. This is the result that we have so far. So basically, we know the value of a1 is pi by 6. So tan square a1 is simply minus 1 by 3 because tan a1 is 1 by root 3. So we have tan square an minus 1 by 3 is n minus 1, right? So I'll go to the next screen. We end up with this equation tan square an minus 1 by 3 is equal to n minus 1, which implies that tan square an is equal to 3n minus 2 by 3, right? Or that implies tan an is root over 3n minus 2 by 3. This is what we have come up with. So if you think about it, sine a1 multiplied by sine a2 till sine am. This is what we wanted to find. Each sine can be written as a tan by sec, right? Think about it. Every sine function can be written as the fraction of tan by sec, right? So we multiply all of them like this. This is tan am by sec am. Now remember what result we got earlier as part of our recurrence. We knew that tan an plus 1 was equal to sec an. We already had that in the beginning, the first step of the recurrence, right? So every sec is tan of the next higher term, right? So this is what? Tan a1, sec a1 is tan a2. And tan a2, sec a2 is tan a3. And so on till tan am, and sec am is tan am plus 1. Notice that everything cancels nicely here. So you are ending up with tan a1 by tan of am plus 1, right? And tan a1 is 1 by root 3, and tan of am plus 1 would be from here, tan am plus 1 is root over 3m plus 1 minus 2. So that is 3m plus 1 by root 3, right? So we have root of 3m plus 1 by root 3. So this is coming out to be 1 by root of 3m plus 1, right? So now we have to say, we have to find a positive integer m such that this product was equal to 1 by 100, which implies 1 by root 3m plus 1 is equal to 1 by 100. So that means 3m plus 1 is 10,000, and 3m is 9999, and m is 3333. So that is our answer for this. So what did we use here? We basically worked with a recurrence equation. We noticed that there is a tan and a sec pattern, so we can use telescoping series nicely. And after that, it was pretty straightforward. We did telescoping series, and the final expression we wrote in terms of tan and sec, right? So that's it for this one. Let's move on to the next question. This one is stated as follows. Assume that a sequence an satisfies a1 is equal to a2 is equal to 1 and an is equal to a square, an minus 1 square plus 2 by an minus 2, and this is true for n greater than equal to 3. We have to find the formula for the general term. Find the formula for an, the general term here, right? Okay, so let's work with the statement here, and we'll get an times an minus 2 is equal to an minus 1 square plus 2. And in this equation, if we replace all the n's with n plus 1, that will give us a new equation. An plus 1, an minus 1 is equal to an square plus 2, right? Okay, now looking at this equation, we can, okay, so we have two equations actually. We have one equation like this, which was the original equation, and we have one equation like this. So if you subtract these two equations, what happens? An plus 1, an minus 1 minus an minus 2 is equal to an square minus an minus 1 square. The two gets cancelled. We are basically subtracting the two different versions of the same recurrence. We are getting this, and we will bring the an minus 1 square term on this side, and we'll take this term on that side. So we'll end up with an plus 1, an minus 1 plus an minus 1 square is equal to an square plus an into an minus 2. Taking an minus 1 common, we get an plus 1 plus an minus 1. And here we can take an common. We get an plus an minus 2, right? So therefore, we have an plus 1 plus an minus 1 divided by an plus an minus 2 is equal to an by an minus 1. This is the equation we have gotten after all these simplifications, right? Okay, so now notice that this is a nice pattern here. This is an and the term before it, and here we have an plus 1 plus an minus 1 and so on, right? Notice here also there is a nice pattern. This term here is 1 less than this term, and this term here is 1 less than this term, right? So I will write it on the next screen, and I have an plus an minus. I have an plus 1 plus an minus 1 by an plus an minus 2 is equal to an by an minus 1. Now, if you replace every n plus 1 with n, this is equation 1. I will get a new equation, which will be an plus an minus 2 by an minus 1 plus an minus 3 is equal to an minus 1 by an minus 2, right? And like this, if you keep reducing one term, every term you are reducing by 1, right? So the next term would have been an minus 1 plus an minus 3 by an minus 2 plus an minus 4 is equal to an minus 2 by an minus 3. Similarly, if you keep doing this, eventually you can end up at here, and it is a4 plus a2 by a3 plus a1 is equal to a3 by a2, right? You can keep constructing new equations like this. What I want to do is multiply all of these equations. Multiply all these equations. Why? Because you will notice that when you multiply LHS, this gets cancelled with this. Similarly, this will get cancelled, and this will get cancelled, and you will end up with an plus 1 plus an minus 1 by a4 by a3 plus a1. This is the LHS after multiplying. On the RHS, you can see again similar cancellations are happening, and you will get a an by a2 here, right? Great. Now, using the initial recurrence formula, an was equal to a square n plus 1 plus 2 by an minus 2 we can put 3 here. A3 is equal to A2 square plus 2 by A1, but A1 and A2 are equal to 1. So that implies that A3 is equal to 1 plus 2 by 1. So that is 3. A3 is 3, right? So now we know A3 is 3, A1 is 1, and this is also 1, right? So basically, what are we getting here? This starts looking like, I will just write it here on the side. This starts looking like an plus 1 plus an minus 1 by 4, 3 plus 1 is equal to an by 1. So therefore, you have an plus 1 is equal to 4an minus an minus 1, right? This is the equation we have right now. So let's simplify this equation and make it look like our general recurrence. So replace n plus 1 with n plus 2. So every n I'm replacing with n plus 1, right? So I'll just write it here. I have this equation. An plus 1 is 4an minus an minus 1. I can replace n with n plus 1. It becomes an plus 2 is equal to 4an plus 1 minus an. Now notice that this is our general uh, form of a linear homogeneous recurrence of second degree. Second degree linear homogeneous recursive sequence, right? So our characteristic equation here is going to be x square is equal to 4x minus 4, right? Not minus 4, it will be minus 1, obviously. This is our characteristic equation, x square minus 4x plus 1 equal to 0. The roots of this characteristic equation are 2 plus root 3 and 2 minus root 3. And these are both distinct roots. So this follows theorem 1. So our an can be written as a1 into 2 plus root 3 power n plus a2 into 2 minus root 3 power n, right? And now our job is to find a1 and a2. And given that a1 is equal to a2 is equal to 1, we get two equations. A1 2 plus root 3 plus 2 minus root 3 a2 is equal to 1. And also a1 whole square of this is 7 plus 4 root 3 plus 7 minus 4 root 3 a2 is also 1. If you solve these two equations, you will get a1 as 3 root 3 minus 5 by 2 root 3 and a2 as 5 plus 3 root 3 by 2 root 3. So finally, our general form of an becomes 1 by 2 root 3, 3 root 3 minus 5, 2 plus root 3 power n plus 5 plus 3 root 3, 2 minus root 3 power n. And in order to check whether the theorem that we learned was valid or not, you can just put n is equal to 1, 2, 3. You should get a1 is equal to a2 is equal to 1 and a3 is equal to 3. And you can even put higher terms and check whether it is fitting the initial recurrence that we have. You will realize that it does fit. Okay. So fine. So we have gotten this one. Let's move on to the next question. Question 3. Let n be a given positive integer. N be a given positive integer. A sequence a1, a2 till an is defined by a0 is half and ak is equal to ak minus 1 plus ak minus 1 square by n for k goes from 1 to till n. We have to prove 1 minus 1 by n is less than equal to an is less than 1. Okay. Now think about the AK here. AK is equal to AK minus 1 common 1 plus AK minus 1 by n. And that means AK minus 1 multiplied by n plus AK minus 1 whole divided by n, right? If I take reciprocals here, I get 1 by AK is equal to n by AK minus 1 multiplied by n plus AK minus 1. And it is obvious from here that this can be split into two terms. I can write it as 1 by AK minus 1 minus 1 by n plus AK minus 1, right? So therefore, I have this nice relation 1 by n plus a of k minus 1 is equal to 1 by a k minus 1 minus 1 by a k, right? This is the result I have gotten. This is coming directly by simplifying this recurrence formula and taking reciprocals and rearranging it a little bit, splitting this fraction and so on. Now this is clearly a telescoping series on the right hand side. So if you put k is equal to 1 to n and add all the versions of it, you will end up with the formula, this formula. Summation of k goes from 1 to n, 1 by a k minus 1 plus n should be equal to, this side will become a telescoping series 1 by a0 minus 1 by an, right? This is what you end up after you add up all the versions of this, right? Okay, so now let's work with this result that we have gotten. We have 1 by a0 minus 1 by an is equal to summation k goes from 1 to n, 1 by n plus ak minus 1. Now since ak minus 1 is greater than 0, right, we have 1 by n plus ak minus 1 is less than 1 by n, right? Therefore, summation of k is equal to 1 to n, 1 by n plus ak minus 1 will be less than summation of k goes from 1 to n, 1 by n, which is equal to 1, right? So this tells us that we have 1 by a0 minus 1 by an is less than 1, right? And a0 was equal to half. So 1 by a0 is 2 minus 1 by an is less than 1. So 1 is less than 1 by an. So taking reciprocals, you get 1 is greater than an. So we have proved one part of the statement that an is less than 1, right? So this part of the problem is already done. On the other hand, we have the recursive formula implies that ak is greater than ak minus 1. Look at the recursive formula. Ak is definitely bigger than ak minus 1 because we are adding a positive quantity to ak minus 1 in order to get ak, right? So therefore, for any k belonging to 1 to n, we have 1 by ak minus 1 no. So because ak is bigger than ak minus 1, we can say that the highest possible value will be an, right? So we can say ak minus 1 is less than an is less than 1, right? So all the terms are less than basically 1, including an is less than 1. That is what we have shown so far. Now let's try to do the other part of the problem. So looking at the formula that we have gotten, 1 by a0 minus 1 by an is equal to summation of k is equal to 1 to n, 1 by n plus ak minus 1. Now it is clearly greater than summation of k is equal to 1 to n, 1 by n plus 1, because we know that ak minus 1 is less than an is less than 1. We just now showed that in the previous screen, right? So now think about this summation. This summation is clearly, there is no k here. So this is simply n by n plus 1. There are n terms here and you keep repeating the same constant. So we have 2 minus 1 by an, because a naught is half, is greater than n by n plus 1. So 2 minus n by n plus 1 is greater than 1 by an. And this becomes 2n plus 2 minus n by n plus 1 is greater than 1 by an, or n plus 2 by n plus 1 is greater than 1 by an, which implies n plus 1 by n plus 2, taking reciprocals, is less than an, right? So an is greater than 1 minus 1 by n plus 2, which is equal to this n plus 1 by n plus 2. So since it is greater than this, it must be greater than this, right? Because 1 minus 1 by n plus 2 is bigger than this. So we have shown here that an is greater than 1 minus 1 by n. And we have already earlier shown that an is less than 1. So our proof is done, basically, right? So that's it for this one. Let's look at the next problem. Question number 4. We have, let a sequence an be defined as a1 is 1 and an plus 1 is equal to an by 2 plus 1 by 4 times an. We have to prove that when n is greater than equal to 2, the numbers root over 2 by 2an square minus 1 are all positive integers. Okay. So we have to prove that the sequence of numbers of this kind are all positive integers. And since there is a root here, it will be nice if we can assume that there is a sequence bn and bn is defined by this, right? Let's assume this as a sequence and we are substituting this. So from here we get bn square is what? 2 by 2an square minus 1. And our job is to prove that all the numbers bn for n greater than equal to 2 are positive integers, right? So if bn square is this, 1 by bn square will be equal to 2an square minus 1 by 2. So 1 by bn square is equal to an square minus half, right? So therefore we are getting an square is equal to 1 by bn square plus half, right? Okay, so let's work on the next screen. We have an square is equal to 1 by bn square plus half. So that implies that an plus 1 square will be 1 by bn plus 1 square plus half, right? Now we have a condition on an, right? So we know that this is true and right. So what we will say is our initial recurrence was what? An plus 1 was equal to an by 2 plus 1 by 4 an, right? An by 2 plus 1 by 4 an. So an plus 1 square from here is coming out to be what? An square by 4 plus 1 by 16 an square plus 1 by 4. This is what an plus 1 square comes from here. So therefore, this must be equal to this, right? So we can write 1 by bn plus 1 square plus half is equal to an square by 4 plus 1 by 16 an square plus 1 by 4, right? And now what we'll do is we'll replace these an. We know that an square is equal to 1 by bn square plus half. So on the right hand side, I will write 1 by 4. An square is 1 by bn square plus half plus 1 by 16, 1 by bn square plus half plus 1 by 4. And here you have 1 by bn plus 1 square plus half. So everything is now in terms of bn plus 1 and bn, right? So if you simplify this a little bit, you should get 1 by bn plus 1 square is equal to 1 by 4 bn square plus 2 bn square by 16 bn square plus 2 minus 1 by 8. I am just simplifying it, nothing major. You should check the calculations yourself as well, right? Again, simplifying it a little further, I'll write it on the next screen. We have so far 1 by bn plus 1 square is equal to 1 by 4 bn square plus bn square by 8 bn square plus 2 minus 1 by 8. Only working on this side, this becomes 1 by 4 bn square plus bn square plus 2 by 8 bn square plus 2 minus 2 by 8 bn square plus 2 minus 1 by 8. This becomes 1 by 8 and cancels this term. So we have this is equal to 1 by 4 common, 1 by bn square minus 1 by bn square plus 2. And this becomes basically 1 by 4 into 2 by bn square into bn square plus 2 here. And that is equal to 1 by bn plus 1 square. So finally, we simplify it out and we get bn plus 1 square is equal to 2 bn square into bn square plus 2. This is what we are getting. So we can write this as 2 bn square, and instead of bn square, we can use the same relation in itself, right? So here we have bn plus 1 square is written like this. So obviously bn square will be written like 2 bn minus 1 square, bn minus 1 square plus 2, right? So what I will do is I will write this stuff here for bn square plus 2, right? So it becomes 2 bn minus 1 square, bn minus 1 square plus 2 plus 2, right? So that can be written now as, to take a 2 common from outside, 4 bn square. This becomes bn minus 1 square whole square plus 2 bn minus 1 square plus 1, which is basically bn minus 1 square plus 1 whole square. And 4 bn square is outside, right? So what we are getting finally is bn plus 1 square is equal to this, right? Which implies that bn plus 1 is equal to 2 bn minus 1 square plus 1, right? Now think about it. Once you have this relation, we can start putting some values. If you look at the original relation, b2 was equal to 2 by 2a2 square minus 1, which was equal to 2 root over 2 by 2 into 9 by 16 minus 1. Why? Okay, I'll just do it on the next screen. So far what we have is bn plus 1 is equal to 2 bn minus 1 square plus 1. And we have a1 was 1, a2 was equal to a1 by 2 plus 1 by 4a1. So a2 is 1 by 2 plus 1 by 4, which is equal to 3 by 4. If a2 is 3 by 4, what is b2? b2 is root over 2 by 2a2 square minus 1, which is going to simplify like this. 2 by 2 into 9 by 16 minus 1, which is equal to 2 by 1 by 8, which is equal to 4. So b2 is 4, right? And B3 is what? B3 is root over 2 by 2A3 square minus 1, which is equal to 24. You can calculate this out because B2 is 4. And actually A3 you'll have to find out. A3 you can find out by doing 3 by 8 plus 1 by 4 times 3 by 4. So 3 by 8 plus 1 by 3, so 24, 9 plus 8, 17 by 24. A3 is 17 by 24, so it is becoming 2 into 17 square by 24 square minus 1. Correct. So this becomes 289 into 2, 578 minus 576 by 576 into 2. This cancels and it is becoming 24. Correct. So B2 and B3 are integers. We are getting B2 is 4, B3 is 24, right? And now we have established the base case. We have this formula for all the higher BNs, right? We have shown that the base case is integers. B2 and B3 are integers. We'll prove by induction, that this is also an integer. So assume that Bn plus 1 is integer till, let's say, n plus 1, and prove that Dn plus 2 is also an integer. I will leave this induction proof to you. The base case is done. We have gotten the correct recurrence for it. Now you just have to finish the last step. So you can try that out yourself. Let's move on to the next one. Question 5. Suppose A is an irrational number greater than 1, and n is an integer greater than 1. Prove that the number a plus root over a square minus 1 whole to the power 1 by n plus a minus root over a square minus 1 whole to the power 1 by n is irrational. Okay. We have to show the irrationality of this. So usually such questions we'll do by proof by contradiction. So before we start, however, we'll denote x is equal to a plus root over a square minus 1 whole power 1 by n. And then it is obvious that a minus root over a square minus 1 whole power 1 by n is equal to 1 by x. Why? You can multiply this with this and you will realize that they are conjugate radical expressions. So the product of them is actually 1. So if this is x, this is 1 by x, right? So let's say we denote ak as x power k plus 1 by x power k, right? With k going from 0, 1, 2, and so on, right? So this sequence, you will realize this sequence ak satisfies the recurrence ak plus 2 is equal to ak plus 1 multiplied by x plus 1 by x minus ak. You should check this. It is very simple to check. You have to prove that x bar k plus 2 plus 1 by x bar k plus 2 is always going to be equal to x bar k plus 1 plus 1 by x bar k plus 1 multiplied by x plus 1 by x minus x bar k plus 1 by x bar k. Now multiply this out, you are getting x bar k plus 2, 1 by x bar k plus 2, but you are also getting x bar k plus 1 by x bar k, which is getting cancelled. So it is very easy to confirm that our sequence AK always satisfies this recurrence, right? Okay. Now if x plus 1 by x is rational, if it is rational, then using a naught is equal to 2, a0 here is equal to 2, obviously, because you will put x bar 0 plus 1 by x bar 0, and a1 is equal to x plus 1 by x. We know that a1 is rational, a0 is rational. So this is rational and a0 and a1 are rational. So any ak is always rational. I hope you understand this step. If this part is rational, then any ak will be built by multiplying rational numbers and subtracting a rational number, right? Suppose you wanted to find out a2. a2 would be what? a2 would be k is 0. So a1 times x plus 1 by x minus a0, right? Now a0 is 2. It's a rational number. This is, we are assuming this is rational. And a1, again, we are assuming it is rational. So then obviously a2 is rational. If a2 is rational, a3 will be rational. So any ak is always rational here, right? For any value of k. So now what happens is, let's assume what happens when you put k is equal to n, right? If you put k is equal to n, what you get is an. An is x bar n plus 1 by x bar n, which is equal to x bar n and 1 by x bar n. If you calculate it, is a plus root over a square minus 1 plus a minus root over a square minus 1, which is equal to 2a, right? So according to our statement, if this was rational, x plus 1 by x was rational, all ak's are rational. So therefore an must also be rational. Therefore 2a must be rational. But in the problem, it has been said that a is irrational. In the problem, a was irrational, so 2a is irrational, and we have come to a contradiction, right? So that means our assumption is wrong. Here, this assumption is wrong. X plus 1 by x is definitely irrational, right? And x plus 1 by x is irrational is what we wanted to prove when we started out itself, right? Okay, so that was this one. And let's look at the final problem. This is a sequence A1, A2 till A201 of positive integers satisfies A1 is equal to A201 is equal to 19,999 and AI minus 1 plus AI plus 1 by 2 minus AI is always constant for I goes from 1 to 200. We have to find the value of A200. That is the question. It's, oh, by the way, I missed one thing, is always a constant positive integer. So the question says that this quantity is always a constant positive integer for I goes from 1 to 200. And we are given two values, A1 and A201, and we have to find A200. So let's say, let AI minus 1 plus AI plus 1 by 2 minus AI is equal to a constant C. C is a positive integer, right? So we get AI minus 1 plus AI plus 1 minus 2AI is equal to 2C, which implies that AI plus 1 minus AI is equal to AI minus AI minus 1 plus 2C, right? We are just rearranging the terms here. Let's denote Notice this is the difference of two successive terms, and this is also the difference of two successive terms. So let's denote di as ai plus 1 minus ai, where I goes from 1 to 200. So this is basically di is equal to di minus 1 plus 2c, right? So this implies that the difference of the di's is always a constant positive integer. So di's form an AP. We can conclude from here that di's are forming an AP, right? And the common difference is 2c for that AP. So that helps us write the general term of di. So the general term of di would be d1 plus 2 times c times I minus 1, right? For I goes from 1 to 200. Now, when I is greater than equal to 2, we can say each term ai will also be constructed like this. It is the sum of j goes from 1 to I minus 1, aj plus 1 minus aj plus a1, right? Think about it. What is this sum? J goes from 1 to n, 1 to I minus 1. So when you start off, you get a2 minus a1 plus, then you get a3 minus a2 and so on till ai minus ai minus 1 plus a1. Now think about it. This is, you combine a1 with this, you get a a2. You combine a2 with this, you get a a3. And similarly, you keep adding, you will end up with an ai. So this is just a fancy way of writing ai, right? But the benefit of this is that this is a dj, right? You are saying ai is equal to sum of j goes from 1 to I minus 1 dj plus a1, right? So that is good because we know the general expression for di, because di is from an AP. So this is basically equal to a1 plus summation j goes from 1 to I minus 1, and dj can be written as d1 plus 2c j minus 1, right? You can do this summation easily, and I will leave it to you. The final summation value of ai will come out to be ai is equal to a1 plus I minus 1 d1 plus 2 times I minus 1 into c. This is the equation that comes for any ai. And obviously, this equation will be satisfied for a1, right? So if you put I is equal to 1 in this equation, you will get that this term is vanishing. So a1 is equal to a1 is coming. And it is also satisfied by a201. So a201 will be equal to a1 plus 200 d1 plus 199c. And that is equal to a1 has been said in the problem itself. A201 is equal to a1. So therefore, we get 200 d1 plus 199c is equal to 0, which means d1 is equal to minus 199c. That is good. We can replace this d1 here. So our formula now becomes, when you replace d1 as 1 minus 199c, our formula for ai becomes ai is equal to a1 plus I minus 1, I minus 201 into c. And because we know a101 will be equal to a1 plus 100 minus 100 c. So it is equal to a1 minus 100 square c. And a1 is 19999 minus 100 square into c is a101. And we know from here that all the AIs were positive integers, right? All the AIs are positive integers. So we know that this must be a positive integer. So that tells us that 19999 minus 10,000 C is greater than 0, and it is a positive integer, right? So this basically tells us 19999 is greater than 10,000 C. So C is less than 19999 by 10,000. So basically you're getting C is less than 2. So that implies C must be 1, right? C cannot be 0 because it was said that it's a constant positive integer. So we get C equal to 1 basically. We are getting it by comparing the value of A101 and making sure that it's a positive integer. So therefore our formula is further simplified. AI is 19999 plus I minus 1 into I minus 201. And we have put the value of C as 1 now. Earlier we had I minus 1 into I minus 201 into C. That was our expression for AI earlier. And from here, we finally conclude A200 is equal to 19,999 plus 199 into minus 1, which is 19,800. So this is a nice problem where you have to use your knowledge of APs and all and your summation and estimate the constants that were unknown, the C's and the AIs and so on. So hopefully you learned something from this video. We have covered a lot of different cases of recurrences, and we have also seen the theorem by which we get the general term of a linear homogeneous recurrence. So that's a good place to stop. See you in the next video.